How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to be taking a lengthy look at OSPF areas and LSAs, or link state advertisements. So we're going to be spending quite a bit of time going over just a high-level overview of what areas are, the different types of routers, the different types of LSAs, what the LSAs are meant to do, that type of stuff. And I will be honest with you that this is going to be probably one of the most pivotal videos in the OSPF section, because at this point in the series in the OSPF section, I really haven't gone into a ton of detail, other than I've configured area 0, which you really don't know what area 0 is yet. I did some basic configuration first just to show you guys how to get it up and running. So if you're like CCNA and you just need to get something done, this is how you do it. So I kept it very, very simple just to get the ball rolling. As a matter of fact, all I did was do what the CCNA blueprint stated, which was configure and verify single area OSPF. We've done that. So we've checked the box for CCNA. So we're going to take a technical deep dive into this. I'm going to walk you through how this stuff works. OSPF is probably one of the most complicated routing protocols there is in terms of its scale, capability, and stuff like that. So when we go through and dig into this, I've taken, I'm going to just quickly scroll through this. I've taken a lot of notes as to what it is that you need to be aware of and how they work. So I've tried to take as much of the guesswork out of LSAs as I can to try to break down what they do, how they work, and all that type of stuff, because it's one of those things where you really need to understand the details of it before you can really go into the protocol and be comfortable with it. So with that being said, we're gonna do some on-the-fly whiteboards where we need to make sure you guys understand what's going on, and go from there. So without any further ado, I'm gonna try to keep this introduction rather short, and we're gonna go ahead and dive right into it. So OSPF areas and LSAs. So areas overview adds hierarchy and scalability to OSPF. An area defines a flooding domain, where how far can you send a routing update. A routing update in OSPF is known as an LSA, or a link state advertisement. All devices in the area agree on the topology. What is the topology? The link state database. So for every network statement you use in OSPF, it is going to generate an LSA, link state advertisement. The link state advertisement is going to be the interface prefix itself, and then that information is going to get added into the link state database and then propagated out to all the other routers inside of the area. Now, I don't want to jump too far ahead, but this is what they refer to as a type 1 LSA. Anything that's directly connected to the router that's generating the update is considered a type 1 LSA. Every router in an area is going to have type 1 LSAs, and each one is going to generate its own LSA type 1s for propagation through the area. We'll talk more about that once I get through some of the more the bigger chunk of information. We'll go into a whiteboard and I'll draw it out. Changes inside the area require LSA flooding and full shortest path first run, or SPF. The goal of OSPF is to solve the shortest path tree to the node that owns the attributes of a prefix. So the idea is solve the shortest path tree to a router LSA. You have at the same time solve the shortest path to the prefix. Essentially, and I think I've mentioned this already once before, that if I want to get to a particular destination, like I think I used snow pants because I like to go skiing in the winter. So I don't go to, I am able to find the ski pants, or the skis, or whatever you want to call it. I'm able to find the winter sports apparel by going to the winter sports apparel store, which has the winter sports apparel inside of it. So the winter sports apparel is what I'm trying to get to, and I go to the store that has that apparel inside of it in order to get there. So the router LSA, the shortest path tree to the router LSA. So if I can figure out if I can figure out which router owns that prefix, if I can figure out which store has that apparel in it. If I can find that store, I can find the apparel. If I can find the router, I can find the network. That's essentially what's happening here. So by the shortest path tree, or the SPT, it's also a multicast term that we'll talk about. But for right now, just understand that you're trying to look in the routing table and figure out from me to you, what is the straightest or shortest path between me and you. If I get to you, therefore, well, I should say, if you're at home, if I drive to your house, you should be in the house. There, if I get to your house, I should be able to find you. Simple as that. Or if you're out and about and I ping your phone and I call you and be like, hey, where are you at? I've called your phone, which is your identifier in the cellular network. You tell me where you're at, and then I can come to you. I can throw as many analogies as you want at this. Essentially, they all mean the same thing. If I can solve the tree to the router that advertises the route, I can then find the route itself. All right. So routing between areas hides topology details. So, and when we get into inter-area routing, which will be coming up here very, very shortly, inter-area routing is similar to distance vector. So the idea here is in area 0 to route to a prefix in area 1, I have to do a couple of different things. You have to solve the shortest path tree from the source to the area border router that advertises the prefix. So what this means is the area border router is going to generate a type 1, or is going to generate a type 3 LSA. A type 3 LSA is going to be a network summary LSA. And if I think I scroll down here, it's the ABR LSA. I think they refer to it as the network summary. Yeah, network summary. Right there. What's going to end up happening is you're going to, and there's going to be a type 3 LSA generated. If I'm in area 0 and you're in area 1, I have to pass through an area border router, an ABR, in order to get that. I have to figure out what the shortest path tree is to the ABR, because the ABR is going to generate a type 3 LSA for every type 1 LSA that's in area 1. Here's a big caveat. Type 1 and type 2 LSAs never leave the area they live in. They're not allowed to. So it's an area-specific LSA. Now, you're going to have type 1 and type 2 LSAs in every area of every OSPF network you ever work in. That's how the protocol works. If I'm in area 0 and you're in area 1, I need to figure out what border router, what area border router I have to get to in order to get to wherever you're at. So if I can solve the shortest path tree to the area border router, the ABR, via the type 3 LSA, because that's what's generated, type 3, the ABR for every type 1 LSA that's in area 1, a type 3 LSA is going to be generated for that type 1 LSA and then going to be pointed to me. I solve that path based off SPF. I solve whatever that is to the area border router. By solving that path, figuring out what routers I need to go to in order to get there, once I get to the ABR, if the ABR will then be like, okay, you need to go over there. And it'll point me to the next router ID that I need to figure out, and the next router LSA. So I can solve the shortest path tree to the ABR. The ABR has already solved the shortest path tree to the router that owns the LSA. And so then I just have to get to him. Now, I want to clarify something. That we are not doing routing based off of router ID. So I know I keep mentioning solve the shortest path tree to the router that owns the LSA. I'm not doing routing based off of router ID. I'm doing routing based off of prefix. So what subnet was advertised? What subnet am I trying to reach? But the way that OSPF looks at it, it looks at who is the advertising router and what is their router ID. Because remember, everybody's got to have their own unique router ID. So if I can solve the shortest path tree from me to their router ID, because their router ID ties to a router LSA, if I can figure that out, I'm able to then figure out how to get to them. So the router ID is not how we do the routing. It's based off the prefix, but inside of the prefix information that we get from that particular router, a router ID is there, and that is how we're solving SPT. So that's essentially how it's happening in the back end. And I'll walk you guys through that. It's going to be very, very straightforward once we get into it, because I know it sounds like, well, are you solving for the prefix or are you solving for the router ID? You are solving for the prefix. So you're trying to figure out what path to get to what path to take in order to get to a particular prefix, whatever subnet you want to reach. Every router is going to have its own ID, the router ID. So if you can solve the shortest path 3 to the router LSA, or in this case here the type 3 LSA if you're in between areas, then therefore you're also going to be able to solve the shortest path 3 to the prefix you're trying to reach. So that's essentially, you're trying to get to the node that owns the prefix. If you can get to the node that owns the prefix is already there. You've already reached the prefix. So once the ABR solves the shortest path 3 to the node that owns the attribute of the destination prefix. So it's almost like a redirect. So when you have this set up where you've got multiple areas defined, changes outside the areas don't always require LSA flooding or SPF. It does limits the impact on the router resources. And this is actually a big deal because I have seen OSPF domains that are very, very large, very, very wide area zeros. And I'm like, oh my God, what are you guys doing? And then they wonder why, if something happens in a remote location, why things are reconverging all the time. If links are flapping or whatever the case might be. And they're like, oh my God, you guys are doing this so wrong. So we'll talk about this, but the reality of it is, if you can break your network up into areas where it makes sense, do that. Because it doesn't make sense to not do that. So we'll talk a little bit about that. We're actually going to talk about that right now. So we have a 2-level hierarchy. We have our backbone area, which is also known as area 0, and used to summarize topology information between other areas. This is not a summarizing the network layer reachability information. The topology summary is different. So we'll talk a little bit about how that comes into play later on. So LSA type 3, the ABR network summary, and LSA type 4, the ASBR network summary. These are going to provide us a summary of what's going on. So this is not an area range, which is NLRI summarization. Traffic from one area to another must go through area 0, and it must be contiguous. So the idea here is this. Actually, let me finish up non-backbone areas. All other area 1 through 2 to the 32nd, or area 1 through area 255, 255, 255, 255, must connect to area 0. So must use connections to area 0 to reach other areas. This looks something like this. Let me go ahead and grab my pen tool out real quick. So I have area 0, and then I have, let's say I have R1 here, and I have R2 here. So I have R3 here, and I have R4 here. These guys all belong to area 0. Now, what will end up happening is I have, let's say I have area 1 here. Let me go ahead and get out of the way. Then I have area 3 up here. Then I have area 2 over here. Then I have area 4 over here. What happens is all of these routers are going to provide summarization in some case. So when we say this, used to summarize topology information in between other areas, there is summarization options available to you, but the idea is to try to limit the amount of routes being propagated. So I'm actually going to come back to this in a little while because I don't want to get too deep too quickly in this before I've talked about how other stuff works. But I'm going to keep that on the screen so we have a reference down the road. So let's talk about the router types. And actually, let me draw one here in the middle. Let me draw R5, and we'll have him connect to R1 and R, and these guys will connect like this. This guy will connect like that. And then we'll have internet. And so we'll have internet will connect. Actually, let me do one more over here. Let's do R6. This is R4. And then we're going to have a connection here. Then we'll have iNet here. And then we'll have iNet there. So the backbone for when it comes to router types is at least one link in area 0. Boom. Problem solved. That's a backbone router. Technically, every router here, R1, R2, R3, R4, R5, are all considered backbone routers because they all have at least one interface inside of area 0. An internal router is going to actually, let me do this. Let's draw R7. R7 is going to have all links in non-backbone area. So R7 doesn't have any links at all inside of area 0. He is inside of area 4. So actually, do this. Draw this a little bit differently here. And then we'll draw that, and then we'll draw that. So area 0 is in the middle. So I'll just draw. I know the color coding is a little bit weird, but it makes sense. So area 0 is here. You got area 3, area 1, area 4, area 2. See if I can't connect. There we go. So you have your backbone routers are going to be R1, R2, R3, R4, R5. Those are your backbone routers. Your internal routers are going to be R7 because all links in a non-backbone area. Area 4 is not a backbone area. An ABR links in both area 0 and in non-backbone area. We will run SPF for every area that it belongs to. It will have SPF databases for each area it belongs to. Connections in 2 areas run SPF twice. And it's used to summarize information between area 0 and non-backbone area. So that means that R1, R2, R3, and R4 are ABRs. Okay? An ASBR, an Autonomous System Boundary Router, is at least one link in one OSPF domain, at least one link outside of the SPF domain. So this could be EIGRP, ISIS, BGP, and it's used to redistribute information to and from other routing domains and OSPF. So R6 is going to be an ASBR, and so is R2. So actually, let me break this up. So we have R2 and R6 are ASBR. And just to reiterate, we have Autonomous System Boundary Router. Well, wait a minute, Rob. I thought OSPF was a linked state protocol and not distance vector, right? Why do we have an or not BGP? Autonomous System Boundary Router simply means that it is the flooding domain. So even though we have different areas, the routes are still flooding everywhere, right? You know, we're not preventing a route on, say, R10 that connects to R1. We have a LAN segment sitting over here. Whatever this guy might be, we'll just say this is, 100. There's nothing preventing 100 from being learned on R6 or on a router in Area 3, right? The propagation is still going to end up happening. So there's still well-known information in every area is flooded everywhere else, right? So that's just one of those other things to keep in the back of your mind is Autonomous System Boundary Router just simply means that you're at the edge of the OSPF domain. Simple as that. So when we talk about that, is it possible for me to take and have R6 as an internet router, have an internet connection, and then redistribute that into OSPF in Area 4? Sure is. What about R2? Can he have an internet connection attached to him and then redistribute a default route into OSPF? Sure can. But we're going to talk about that here in just a minute when we talk about how area type will change how OSPF forwards traffic. So I'm going to go back over here to my arrow. We're going to work our way down here. And let me go ahead and clear this. All right. So let's talk a little bit about the LSA types, because there's a whole bunch of them, right? When it comes to LSA types, we have types sent and received depend on three different factors: the router type, the network type, and the area type. So let's talk about the different types of router types. Or these are specifically going to be these are the LSAs. So we have type 1 router LSA is going to be a directly connected interface on a router. So this guy right here. This is going to be a type 1 LSA. This will be a type 1 LSA. Any interface on any router in any area of OSPF that is directly connected to that router and is advertised into OSPF is a type 1 LSA. Don't ever forget that. So every router is going to be generating type 1 LSAs. It can't not. It's impossible for it to not generate type 1 LSAs if it's going to be participating in OSPF. You have to. There's no getting around it. Type 2 DR LSA. This is going to be where you're going to have type 2 LSAs where you're going to have the DR BDR election. So again, this is going to be if you're running broadcast or non-broadcast multi-access. There's going to be a type 2 LSA generated. Now, do you have to do that? No. If you choose to run point-to-point on every network type, point-to-point on every interface inside of OSPF, then you're never going to see a type 2 LSA. And we're going to go take a look at what that looks like to completely remove type 2 LSAs and not have a DR BDR election process. We're going to do that. But this is just one of those things where it's there out of the gate because Ethernet will be the detected media, and Ethernet is a broadcast media by design. So therefore, it's automatically going to associate it to the broadcast media type. I don't have the ability, without doing some sort of wizardry of doing serial interfaces. I could throw this into GNS3 as a small topology and show you what that's going to look like, and do point to multipoint with frame relay. But the reality of it is nobody does that. So not to say you won't see it in the real world, but it's one of those things where if you want to see what any of that type of stuff looks like, go look up some of my older content where I did CCNP a while back, probably 4 or 5 years ago at this point. Probably longer than that. Probably closer to 10. But go back to my older content, and I do go into that detail, and I talk about how frame relay comes into play and all that type of stuff. So, continuing on. Type 3 LSA is going to be the area border router. So again, R1, R2, R3, R4, these guys are going to be ABRs. Now what's going to end up happening is these guys are going to generate type 3 LSAs for routes coming from area 1 going into area 0. And then they're also going to generate type 3 LSAs from any routes coming from area 0 to area 1. Now what about routes from area 1 passing through area 0 going to area 3? Same thing. If area 3 has a prefix in it that's a type 1 LSA, R3 is going to receive that and then generate a type 3 LSA to send to area 0. Area 0 is then going to take that and advertise it to R1. R1 is going to advertise that as a type 3 LSA to area 1. Then you have type 4, the Autonomous System Boundary Router, the ASBR. Again, this is going to be any connection outside of the OSPF domain. We have two ASBRs. We have a R2 and we have R6. Now, I want to talk real briefly on this because it's going to be interesting, and before I finish out, we're going to end up seeing how this comes into play depending on how you recurse to the default route. So by default, you are going to end up having an internal destinations. So, and then you're going to have type 4 LSAs are going to generate for inter-area external destinations. So what I really want you guys to understand is if I have move this back up here. If I have a scenario where area 0 has a default route, it's going to automatically, for area 0, it's going to try to choose to go to the inter-area external. Meaning it's going to go find the closest type 4 LSA it can get to. In the event that R2 goes down, then anything in area 0 will try to point to the inter-area external. So you're going to always choose your local area type 4 LSA before you ever try to go to an inter-area external LSA. So the idea is this: if I'm in area 0 and I want to get to the internet, I'm going to go via R2. If I am R4 and I'm trying to get to the internet, I'm going to go which way? Again, I'm going to go out to this internet connection right here because it's an intra-area external. You're always going to choose to go, well, we'll talk about this and how the OSPF state machine works, and you're always going to try to stay within your area unless you have no other choice. So now if area 1 here is going to go, which way would he would go? Well, because it's kind of a wash, right? If area here we have area 1, well, what area do you have to pass through in order to get to area 4? You have to go through area 0. So if I'm in area 1 and I need to get to the internet, which way am I going to go? Boom, you guessed it. I'm going to go and jump over to your area 0. I'm going to go out R2. But if I'm in area 4, which way am I going to go? I'm going to go R6 because it's an intra-area external. So, well, what if R6 goes down? Well, it's easy. R4 is just going to send it to area 0 because he's got an inter-area external. He's going to point to R2. But what happens if R2 goes down for the entire environment? Sweet, no problem. R6 is still up. R4 is still advertising the prefix into the rest of the OSPF domain. Area 0 learns it. Area 3 gets it. Area 3 points to R4 because he is the next ABR. Type 3 LSA is being generated. And then R4 has an ASBR route to R6. So everybody will then flow through R6. That's how OSPF will work with default routes. So now that we understand that, it makes a lot more sense. Now let's talk a little about the external LSAs. External LSAs are anything that's redistributed into OSPF. So what ends up happening there is I go into OSPF, and let's say I have a default, static default route pointing to the internet on R2, and I want to get to the internet. Well, I'm going to go ahead and I'm going to redistribute static into R2 from R2 into OSPF, and that's going to get propagated everywhere. That would be a Type 5 LSA. If you notice, there's we jumped right to Type 7. What happened to Type 6? Is nobody like Type 6? Well, Type 6 is the multicast OSPF, and Cisco devices do not support multicast OSPF. So I don't know anything about it other than the fact that Type 6 LSAs do not exist on Cisco hardware. Type 7 LSA is the not-so-stubby area external. This means that you're in a stub area. This is the only time you can redistribute into a stub, by the way. If I have redistribution required in a not-so-stubby area, what I need to do is I need to go through and configure this so that I can allow redistribution into the stub area. Now, it's referred to a not-so-stubby area because there's external access outbound. And here, there's an interesting caveat with this. And I actually talked to some of the guys. I went to Cisco Live 2018, 2019, and I was able to World of Solutions, and I was walking around, and I met some people that I watched plenty of Cisco Live videos on. And so one of the things that I came to find out was that Type 7 LSAs, Type 4 and Type 5 LSAs both point to outside of the OSPF domain. Type 4 and 5 LSAs are not allowed in stubby areas, whether it's totally stubby, or whether it's stubby, totally stubby, not so stubby area, or totally stubby area. Type 4 and Type 5 LSAs are not allowed in stub area types. So, in order to fix that, Type 7 LSAs were generated. A Type 7 LSA is identical to a Type 7 LSA, or to a Type 5 LSA, except for you can't give a LSA a Type 5 in a stub area, so they came up with 7. Type 7 LSA gets redistributed into OSPF and into the stubby area, because a 7 is not a 5, right? And then, so for example, if area 4 was a not so stubby area, and when I was redistributing on R6 into this, so this would be a not so stubby area, I would redistribute the Type 7 LSA into area 4. Area 4, R4 would get it, and then because he's an area border router, he would convert that doing the type 7 to type 5 translation. What he would do is he would translate it from a type 7 to type 5 LSA because type 7s can only exist in not so stubby areas. In order for it to live anywhere else in the network, it has to be translated from type 7 to type 5 because type 5 LSAs are allowed outside of a not so stubby area. And that'll get propagated to area 0, 1, 2, and 3. So we'll see what that looks like as we get down further down the road. But as you can see, that's basically how that comes into play. So let's talk about LSA and route types. There are 3 groups. You have intra-area routes are always going to be a capital O for OSPF. This is going to be your type 1 and type 2 LSAs. They will always exist inside of the intra-area routes. They will never exist outside of the area. So again, you'll never see a type 1 and type 1 or type 2 LSA for a particular area existing elsewhere because they're not allowed to propagate between the area that they live in. They are area-specific LSAs. However, every area is going to have type 1 and type 2 LSAs. But in order to get between areas, to move between on an ABR, you are going to use a type 3 LSA. So type 3 and type 4. So this is going to be your inter-area route. So if you see this, a single O means that it's an intra area, what's inside of the same area. When you see O space IA, this is going to be an inter area, between areas. So we have type 3 and type 4. Type 3 is used to reach inter-area internal destinations. So if I'm in area 1 and I want to get to area 3, I pass through R1, which is an ABR. I'm a type 3 LSA now in area 0. Router 3 is an ABR. He learns that from area 0. He then takes that and he also propagates a type 3 LSA into area 3. So keep that in mind. Type 4 LSA is used to reach inter-area external destinations. So if I'm in area 0, 1, 2, or 3, and I want to get to, this will work for, this will only really applies to, it applies to router 2 as well. But if I'm on R2 and I redistribute a default route into OSPF, I'm also generating a type 4 LSA. But the type 4 LSA will only exist for R1, area 1, R3, area 3, and R4, area 4. Inside of area 0, I'll see just type 5. If I'm inside of area 0, I see just a type 5 LSA because I'm already in area 0. R2 has a link inside of area 0, so therefore he's a backbone router. Because he's a backbone router, I will find a type 5 LSA to reach the internet. Now what's interesting is you won't see 4 show up in your routing table. You'll see type 3, which would be an OI route. So when you see type 3, if you see OIA, it can be 3 and 4, but you're going to be doing, if you're going type 3, which means it's internal, right? You'd have to look at the OSPF database for the specifics. If it's a type 4, you're going to a different area to reach an external path. So to super simplify this, I shouldn't say super, to simplify this, if it's a type 3 LSA, and if you're not sure if it's internal or if it's a type 3 or a type 4, where are you trying to go? If you're in area 1, you're trying to get to area 0, so it's an internal destination, it's a type 3 LSA. If it is a type 4 LSA, so like a default route to get somewhere else, or you redistributed from EIGRP or BGP, any other routing protocol into OSPF generates a type 4 LSA as well. Now, who generates a type 4 LSA? Anybody? Any guesses? The area border router. The area border router generates a type 4 LSA because because inside of this area, this is a type 5 LSA, right? And we're assuming that there's no stub, no nothing. We'll talk about that more in detail when we get into stub routing. But R6 is redistributing a default route or doing redistribution of something into OSPF. So for him, these are all type 5 LSAs inside of area 4. They're all type 5 LSAs. When it gets to R4 and it gets propagated into area 0, router 4 will then generate a type 4 LSA to the rest of the network because he's an area border router and he has an inter-area connection to an external destination. That's how the difference comes into play. So if you're in area 1, 2, 3, or 0, and you want to get to the to something over here, what I will actually do to simple, if this was my topology, what I would do is I would create a loopback address on this box, and I would advertise that as EIGRP. I'd throw it into EIGRP and I redistribute. Sometimes that works. You might have to actually do an extra connection here, or R7. I would take that out of OSPF and put it into EIGRP, and then I would do, form an EIGRP adjacency between R4 here, or something like that. I'm trying to think back if I actually made that work or not. I can't remember. But, so, the caveat is, that should work. If I have an EIGRP connection outbound, yeah, if my logic is right, which I'd have to test it out to see, because it's been a long time since I've had to do such a small demo. This is actually a small topology for doing OSPF. I like doing a bigger topology for OSPF because it really drives home the point. But what ended up happening is, if I was to create a loopback and throw that loopback into EIGRP or BGP, or BGP wouldn't work. I need EIGRP or RIP. Advertise it into EIGRP and then redistribute EIGRP into OSPF. I want to say that would work. I don't know. I'd have to double check. But anyway, not very important for our discussion. But if there was something attached to R6 that was OSPF, EIGRP, BGP, IS to IS, RIP, static route going somewhere else, inside of Area 4, that would be a Type 5 LSA. It would be just an external route. Now, what ended up happening is when R4 gets that, he would generate a Type 4 LSA, and that would get sent to Area 0. Area 0 would then propagate that to R1, R2, and R3 for Areas 1, 2, and 3. Now we talk about E1 over E2 versus N1 and N2. So, interesting way of looking at this is E1 is preferred over E2, and N1 is preferred over N2. However, E2 is the default, and N2 is the default. So you always start there. So both are external LSAs. Exception is Type 7 LSA comes from the not so stubby area. We'll definitely be taking a look at stub areas in more detail in later videos. So if I go E2 and I go N2, what's the difference between the two? What's an E2 versus an N2? Well, what's an E1? What's 1 versus 2? What's that case right there? So the difference between the two is how the OSPF metric is incremented. So if I have E2, that means when I redistribute into OSPF, I automatically associate a metric of 20 to that. And because it's a Type 2, an external Type 2 route, its metric never increments as it flows through the OSPF domain. So if I go on R2 and I redistribute a default route into OSPF, well, I redistribute that default route into OSPF, it gets propagated. It gets propagated with a metric of 20 and an AD of 110, because that's OSPF's administrative distance. It gets propagated into every router in the area, and every router, and no matter how far away from R2 it gets, its metric never increases. If you have a scenario where you want to do another connection and you want to propagate the default route, but you want to consider the cost to get from the ASBR to other parts of the network, you want that cost to go up, then you would go Type 1. So if you do an E1 route, it's going to be more preferred, but the cost goes up. Here's the interesting thing about that. When we talk about this from a high-level overview, you're always going to choose intra-area routes over inter-area routes. So let's talk about, did I have that laid out here? I don't have that detailed out here. But let me talk about it real quick since I'm right here. So the way that I want you to think about this is this. In the OSPF finite state machine, and which LSA do you take? it's going to be from top down. So you're going to always choose an OSPF internal route first, then an OSPF inter-area route second. And then you're going to then choose OSPF E1, then OSPF E2, then then N1, then OSPF E2, then OSPF N2. That is the order in which you're going to choose routes. It does not matter the cost. So if I have a scenario where I did this with a customer a few months ago, where they were receiving, so high level detail is they had DC1 here and they had DC2 here. And they had their campus here. They had connections to each data center, and each data center had internet connectivity outbound. So I'll just put, iNet here. We'll do I1 there, and we'll do I2 there. So DC1 was their primary, DC2 was their secondary, and they're working their way to moving to DC2 as their primary. Right now, internet goes this way to DC1. They wanted to change that to make to advertise internet for both data centers, and they wanted to choose DC2 as their primary. So what I said, cool. What I'll do is on here, because on the DC there's an edge and there's some redistribution points and stuff like that. Well, what I'll end up having to do is go over here and I'm going to say we're going to advertise the default route from here was being advertised as an E1 route because it's the most preferred, right? E1 over E2. And I said, so what I'll do is before I do any redistribution or route advertisement from DC2, I'm going to change this to an E2 route. Then the rest of the OSPF domain will get that update. And then I will then propagate the E1 route. Once I propagate the E1 route, then the E2 route will no longer be used. It'll still be in the database, but it will be a secondary prefix. So then everything will start going this direction for internet. Internet will go DC2 and then out to the internet at DC2 there. I said, so the major thing is you've got firewall sitting over here next to the internet. What will end up happening is anybody that's currently using internet going out DC1, that internet connectivity will stop. And then everybody will start using internet connectivity at DC2, which means those firewalls over there need to be in sync, meaning all the same configuration rules that are on DC1's internet firewalls need to be updated and added to DC2's internet firewall rules. So that when you're sending traffic out the new internet, you're not going to run into any problems. Now, will that cause any hiccups? Yes, it will, because you are changing firewalls. If I am moving from firewall A to firewall B, if I'm streaming live music or whatever the case, anything that's real time, video, voice, that type of stuff, there will be a short interruption there. So when the change was made, we made the change, it went through without a hitch, the configuration was put into place, and by the time it was all said and done, we had a few people, be like, all I had to do was refresh my browser. I had a YouTube stream going, and I just had to refresh my browser. Within a few seconds, I had the video was streaming again. So that's what you end up having to do. So when we have those situations, you can change the way that OSPF routes based off of the type of LSA you're using. And the same thing works for N1 and N2. The only difference is you would do that in a not so stubby area. That's it. So they worked identically. Now the other thing too is with this one here, the cost goes up. The cost does increment. Over here, the cost stays the same. It doesn't go up, it doesn't go down. So you might say, well, if the cost goes up on your E1, how come and if the cost doesn't go up on E2, why does E1 win if the cost is higher? Simple, because regardless of what it is, if they were the same, if you're doing E2 on both, then you'd be ECMP. If you're doing E1 and E1 on both sides, you'd be doing ECMP. But then you'd be able to set the cost value, right? You'd be able to set the cost on a particular link, and then that would adjust your routing in a particular direction. So by using E1 on one side and E2 on the other, if something happens at DC2's internet, then you're automatically going to fail over to E2 for DC1's internet. I said that's the piece that you need to understand here. So failover will be seamless. And they were like, okay, cool. So we put it into place, and it worked as expected. So it worked out quite well. So that's where E1 and E2 come into play. remember the cost goes up, but from a state machine perspective, E1 will be chosen over E2, and N1 will be chosen over N2. Now, by default, it's these are the defaults, E2 and N2. There's no cost incrementation when the route gets propagated throughout the rest of the network, so just keep that in the back of your mind. But I wanted to walk you through that, because that's when I look at scenarios like that, that's the first thing I think of. I was like, well, I'll just use a different external route type. I'll just change your metric type to your metric type E1 versus E2. That's all I'm going to do, and it's a very, very easy transition. So it makes your job as the engineer that much easier to work with. Let me go ahead and pause real quick, and I'll clean up the topology a little bit. All right, so what I want to do now is I want to talk about a little bit of a deeper dive onto the LSA types, because this is where it gets interesting. I'm going to keep the state machine there, and I'm going to keep the topology there for reference. So I'm going to go ahead and get out of the way, though. So LSA type 1 is a router LSA, generated by every router in the OSPF domain, not flooded outside the area they originate in, and has an area local scope. It describes directly connected links, what are my link costs, and who are my neighbors. Type 1 router LSAs are used to build the graph for intra-area SPF. Then we get into Type 2 LSAs, the DR LSA. This one can be turned off if you use point-to-point network types. Generated by the DR on broadcast non-broadcast network types, not flooded outside the area they originated. Describes who is adjacent with the DR. What is my link cost to the DR? Implies my link cost to all other adjacent to that DR. The DR is a central point on the segment. If you can reach the DR is able to reach all other routers on the segment. This means if you can reach the DR, you should have reachability to other routers on the segment. So this affects how you can form adjacencies with and exchange routes with. So all the routers form adjacencies with the DR. All routers don't form adjacencies with all other routers. The DR is used to reduce the amount of redundant info in the database. So essentially, it acts like the BGP route reflector. So instead of you having to form adjacencies with everybody, receive full SPF databases from everybody, and then having to, I should say, link state databases, and then run SPF, it's trying to optimize the amount of communication. The reality of it is, most of the time you're not going to have multiple connections to other devices. It's going to be a fiber or an Ethernet run between two different devices with a /30 point-to-point connection. So you're going to want to change your network type to point-to-point in order for that to happen. You're not going to do a bunch of broadcasts. Now, I'll be honest with you, that's the optimized way of doing things. The reality of it is, people will do the network statement, a very, very wide one. I commonly see RFC 1918 address spaces and OSPF, where they'll do a network of 10/8, 172.16/12, and then do a 192.168/16, all in area 0, because they don't want to have to, if networking is not their main thing, or if it is, but they've got a bunch of other stuff going on, they don't want to waste their time trying to get down to nitty-gritty details. So they bring in folks like myself that know how to do that. We analyze the network, and then we make adjustments based out that information to try to optimize the routing. So what you don't want to have, though, I laugh at this because it happened not too long ago, where I had routers that were at the edge with a point-to-point connection between them. It was a 210 gig port channel, and they had 5 or 6, at least I can remember, 5 or 6 OSPF adjacencies between the two, and it was just like, why? Why are you doing it that way? But anyway, it happens. So, and that's because of the fact that they were not using passive interfaces, they weren't doing any type of stub routing. So, you take the good with the bad, and you try to make the bad as good as you can make it. Alright, so let's dive into the Type 3 LSA. LSA Type 3, the summary LSA, generated by the area border router, or ABR, flooded from one area into non-backbone areas and vice versa. Describes ABR's reachability to links in other areas. It includes cost but hides ABR's actual path to destination. SPF not run for ABR advertised routes. So The ABR can reach a link via shortest path tree and cost X. I can reach the ABR via shortest path tree and cost Y. Implies I can reach the link via shortest path tree and cost X plus Y. If you can solve the shortest path tree to the ABR and the ABR solves the shortest path tree to the destination, then you can reach the destination. This is why inter-area routing looks like distance vector, because you don't get to see everything. The link state databases between areas is summarized into type 3 LSAs. So you don't see type 1 LSAs. You see type 3 LSAs. So, but you run SPF per area. So if you're running the calculation, you're running it for your area, but you're receiving routes pre-calculated for another area, and you're just incrementing the cost. So that's one of those things to keep in the back of your mind when you're scaling OSPF, is that in the event that if a link in area 3 flaps, and you've got areas defined, let's scoot this up just a little bit. If you got a link flaps in area 3 is going to hear about this. Not area 0, not area 1, not area 2, not area 4. You don't care. Now, if this was all one big area and the link flapped in area 3, everybody would hear about it. This is why breaking up into areas makes more sense. Type 1 LSAs will generate SPF inside their area, but that information is not propagated up here. Unless that link goes away, and then R3 will retract or remove the SPF, or I should say the type 3 LSA for that particular prefix. So keep that in the back of your mind as well. The type 4 LSA, generated by the area border router. So again, an ABR generated LSA, flooded from area 0 into non-backbone area and vice versa. Describes ABR's reachability to ASBRs in other areas. Includes cost but hides ABR's actual path to destination. The shortest path first, not run to reach inter-area ASBR. So again, going back here, the SPF is not run for ABR advertised routes. So I want to make sure everybody understands this. If you're in area 3 and a link flaps, or you're generating a new route, you take that information and you calculate it with inside of your area. SPF does the run on the area type 1 LSAs. That information is all figured out. R3 gets it. R3 is then going to just say, here's what I have. Your area 0 is not going to run SPF on type 3 LSAs, because area 0, because there's a link on R3 that's in area 0. R3 and area 0 is a type 1 LSA. It's already been calculated by the local area. So because you already know how to reach R3, you're just going to accept whatever R3 is advertising for you, and that goes for any other areas as well. So you don't do a calculation for inter-area routing, because you've already calculated your path to the ABR. Because you've already calculated your path to the ABR, therefore you're just going to accept whatever the ABR advertises you as type 3 LSAs and type 4 LSAs. So the idea is this. So ABR can reach ASBR via the shortest path in cost X. I can reach ABR via the shortest path tree in cost Y. Implies I can reach ASBR via the shortest path in cost X plus Y. Inter-area external routing is also like distance vector. If I'm over here, so there's a question, would R1 generate a type 4 LSA? It would. It would generate a type 4 LSA for all of this, because, well, actually, no. Actually, yes. Yes, it would. Because if I'm over here, I get an ASBR, goes type 5, and then it goes, yes, it would. So would R3. Anytime you have an external path to something else, you're going to do there's going to be a type 5 LSA in the area 0 link state database. R1 will get the update, and he's an ABR, so he'll translate to a type 4 LSA for area 1. R3 will advertise an ASBR for type 3. So you are correct. Type 5 external LSA, generated by the ASBR, flooded into all non-stub areas, and that's key. We haven't gotten to stub routing yet, but we will. Describes routes ABR is redistributing. So we have a couple different metric types. We have E1 and we have E2. Then we have the forward address. What is the forward address? The forward address is who should I route towards to reach the link. Usually the ASPR itself, but it could be someone else in some designs. Advertise the route that you will tell. Advertise the route to you, but tell you to use another router to reach the destination. I send you the route, but tell you to use another next hop. So it's very rare to have a different forward address. You can change it. I'm not going to be demonstrating that. It's one of those things where you have two entry points to a external path, and this guy right here is advertising it, but you really want this guy to be used. You're changing the forward address to him. That's all that really basically comes down to. So that's essentially what that means. Then you get external type 1 and type 2. So external route type controls how metric for external link is calculated. Type 1 is take the cost the ASPR reports and plus the cost to the ASPR. Cold potato routing. So you're going to route this way. Where type 2 is take just the cost to the ASPR reports in. If there is a tie, then take the cost to the ASPR as well, hot potato. Type 1 is preferred over type 2. So that's the bottom line there. So just remember that the cost is incremented with type 1, the cost is not incremented with type 2. Hot potato routing. Find the closest and fastest point off the network and ship the packet that way. Cold potato routing is find the most optimal internal route through your network and make the forwarding decision that way. And then we have external route calculation. This is what I talked about a little while ago, but I wanted to reiterate it. Performs like this inspector similar to inter-area calculation. So, can I scoot this over just a little bit? There we go. So we have our intra-area external. ASPR could reach link A and cost X. I can reach ASPR via shortest path tree and cost Y. I can reach link via shortest path tree and cost X plus Y. Recursion works like this. A type 5 LSA is advertised to a node in the graph. If a source wants to reach the external destination, it has to recurse to the type 1 to type 5 to reach the ASPR. From the ASPR, you have to recurse to the external route to reach the destination. Essentially, this is my way of trying to overly complicate the explanation. This is definitely a CCIE brain at work here. The idea is I need to figure out, I'm in the area, right? So I'm in area 0 and I have an external route out via type router 2. Router 2 has a type 1 LSA for me to get to. So let's say I'm on R5. I use my type 1 LSA to figure out how to get to R2. Then I get to R2, then I use the type 5 LSA to get to the internet. That's essentially what that's saying. So, my overly complicated way of explaining things. Inter-area externals. So ASPR can reach link A and cost X. ABR can reach ASPR via SPT and cost Y. I can reach the ABR and via SPT, shortest path tree, and cost Z. I can reach link A via shortest path in cost X plus Y plus Z. Recursion works like this, and I laugh at this because it's basically reiterating what I just mentioned. A type 5 LSA is advertised to a node in the graph. If a source wants to reach the external destination, it has to route to the ABR. The ABR then has to route to the ASPR. Then the ASPR then routes to the external destination. So recurse from type 1 to type 3. So you go from your internal router to your ABR. So that's type 1 to type 3. Then from R3 to, say, R2. And then from R2 to the internet, to type 5. That's how that comes into play. So that is how OSPF works at a high level when it comes to areas. I laugh at that because it's now that I'm reading back through this, like, wow. But that's how my brain was interpreting these things, and I know I'm not wrong because I've done this hundreds of times. So not this video itself, but I've done intra and inter-area routing a bunch of different times for a bunch of different customers. So I know how OSPF works in that regard. So it's a lot to take in, and I understand that. So this is definitely going to be one video where it's obviously long. We're at an hour now. So if you guys have any questions, comments, concerns, feedback, drop that information in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.